And something that will come up later in the presentation is software that I will use at the end of this presentation to go through at least one example with the ASHRAE calculation, ASHRAE 62.2-2013 version. So we'll talk more about that as we go along. This webinar, there's an outline of the webinar on your screen now. By the way, there are some seats up front here if you can't find any in the back. We're going to talk about the history and the future of ventilation. The history is very, very long. There's been concern about this for centuries. I will go over the programs, significant programs that are currently requiring ASHRAE 62.2. We will, of course, go over the design details of the ventilation standard for existing buildings. It's quite a bit easier to design ventilation using the standard for new buildings. It's more difficult for existing buildings. And it is my assumption that most of you who are taking part are interested in existing dwellings. We'll look at additional selected requirements of ASHRAE 62.2, and we'll do at least one example calculation with the Residential Energy Dynamics RedCalc-free software at the end of our time together, just before the open question and answer session. A bit of history of ventilation, primarily in the United States. I love this. This is a cover, December 1931. I like it because it gives us a sense of the history, and that back then there was a great deal of controversy about ventilation. What's the best way to ventilate? And you can see by the road sign that the New York Commission was involved with this. Air conditioning industry was involved with this. The air conditioning industry was developing at the time. And this was a controversial issue back then, as it is today, and my guess is that it will continue to be controversial. Recent ventilation standards, these are all from ASHRAE, and by the way, ASHRAE stands for the American Society of Heating, Refrigerating, and Air Conditioning Engineers. And the number designation ASHRAE is given to the ventilation standard is 62. It's rather random, but that's the ventilation standard. The 1973 version of the standard called for 5 CFM, cubic feet per minute per person, and recommended 15 to 20 cubic feet per person. 1981, there was a continuation of 5 CFM per person. ASHRAE 62, 1989. Now this is a significant year, as you can see from the final bullet on this slide. This is the what the BPI Building Airflow Standard, the BAS, is based on. And this version of the standard called for 15 CFM per person and 0.35 air changes per hour. Some of you are probably still using this out in the field, but this will change within the next couple of months if you are following the appropriate BPI standard. And I will say more about that as we move through the presentation. There was a fairly significant change as of 2003 with the ASHRAE standard. Notice now it's 62.2. The ASHRAE numbering terminology uses a 0.2 for residential standards and a 0.1 for commercial standards. So before 2003, it was just ASHRAE Standard 62, which covered both commercial and residential. As of 2003, the standard was split. So there's 62.1 for commercial and 62.2 for residential. By the way, the 62.2 committee was formed in 1997 and it took quite a few years. It was a very contentious time to come up with the first version of the ASHRAE standard. And I hope you can see here the basic equation for ventilation, residential ventilation based on the 2003 standard was 1% of the floor area plus 7.5 times the number of bedrooms plus 1. The bedrooms plus 1 is considered quite a good way to determine the number of people living in the house. The assumption is that 2 people will be living in the master bedroom and 1 person in all of the other bedrooms. There were other versions of the standard: 2004, 2007, 2010 was a significant change. You can see many of you have been using that, and the Department of Energy has been requiring low-income weatherization programs to use the 2010 version now for a couple of years. You can see we have the same basic equation. This is green here to distinguish it from the 2013 version down here below. The 2010 basic equation is the same as the 2003 basic equation. And as I said, the 2010 version was adopted by the Department of Energy and some other organizations.
Rick, we have a question at this point with
Yes.
regard to 62.1. One person asked specifically what's the formula for 62.1. I believe it's a little bit in depth, but could you just touch on 62.1?
Yes, I will, Bill. Good question. 62.1 is a much more complex document, and there are different, generally speaking, to put it in a very simplistic way, there are different ventilation rates required for different uses. For example, office buildings are specified, school buildings are specified. There are some manufacturing processes that are specified, retail areas, multifamily areas are specified, and because of the concentration of the number of people for these various uses can vary significantly. There, generally speaking, are different ventilation rates for different commercial uses. So that question is difficult to answer in a specific way. One has to look at the actual use of the building. The 2013 version is the most recent, and as you might be able to tell from the dates here, the ASHRAE standard is updated and reprinted in its in a full edition every 3 years. The next one will be 2016. The 2013 version was released just before mid-year of this year, and as you can see from the basic equation, there's a bit of a difference. Rather than 1% of the floor area, as we had with the 2010 version, it's now 3% of the floor area because something called the default infiltration value was eliminated. The members of the committee felt that this gave us a more level playing field for the various structures we're looking at. And you'll see in the next slide or one after that how the 2010, 2013, and 1989 standards compare.
We got another good question here. Sorry to interrupt. We
Yes,
got
Bill.
another good question.
Yes.
Are there studies that support the change in ventilation? And if so, are they available or could you reference them?
I would have to, I can't cite those studies, but something that we're doing, something that's coming up, something that the committee is doing, that's what I mean when I say we are doing, is looking at equivalency. And another aspect of this is that the 62.2 standard is a continuous maintenance standard, so we must keep looking at things and making it better. I can get back to you, Bill, with an answer to that question regarding research. I can think of one that was done in California, and I can say a little bit about that on an upcoming slide because one of the major concepts is included on that upcoming slide, but I don't recall the name of the paper, but it's from, it was done at Lawrence Berkeley Laboratories.
Gotcha, thank you.
2012, I think.
Okay.
The last bullet on this slide, the last red bullet, it's important for those of you working under the Building Performance Institute and or the Department of Energy program, such as the Low-Income Weatherization Program. BPI and DOE will be, both organizations will be adopting the 2013 version of the ASHRAE Standard in the year 2014. And more details about that very soon in my presentation. You can see the over time. I hope you're able to see this. This is the source for this graph is at the bottom of the slide. You can see how required ventilation standards have gone up and down. There's a battle here, it seems, as I think all of you understand, between health or indoor air quality and energy. And this battle, I think, will continue as time goes on. As energy, if you look at this in more detail, sometimes if a more detailed chart like this, what you would see is that as the price of energy goes up, sometimes that has an influence on the amount of ventilation required. That can go down. And then energy goes down and the amount of ventilation might go up. It's important for you to know that the ASHRAE committee does not look at energy issues. That's not a direct topic that the ASHRAE committee looks at. We look at indoor air quality primarily. For comparing the standards, as I mentioned just a moment ago, as if we look at a 2,000 square foot, two-story dwelling in Cleveland, I chose Cleveland because that's where I was born and raised, with 4 bedrooms, and we'll look at it in fairly tight 1,300 CFM50 blowed or test, and then we'll tighten it to 1,000 CFM50. So we're looking at it here with 2 different tightness levels. And then below that, the second major bullet, you see the ASHRAE whole building ventilation required. For the 62-1989 standard for 1,300 CFM50 building, the required ventilation is 16 CFM. However, if we tighten it to 1,000 CFM50, it goes up significantly, about 3.5 times to 56 CFM required. The 62.2-2010 standard, if we calculate that, we get 38 for the 1,300 CFM50 building and 47 CFM required for the 1,000 CFM building. As we tighten the building, there's not as much of an increase in goes up by about 25%, not as much of an increase in the ventilation required. And the 2013 version, you see that we have 45 and 57. So the 2010 and 2013 versions are in the same ballpark, certainly. And in some cases, they're very, very close, just a few percentage points different. In other cases, they might be further apart. Natural ventilation is variable, and this is part of one of the red calc-free tools, the advanced infiltration tool. And the chart that you see is for Denver, Colorado. It's a 1400 CFM 50 two-story building. The thermostat is set at 68 degrees, and the date range I looked at, you can set the date range with the tool right here. There's much more to the tool than this, but what I did, I took the chart and I superimposed a 50 CFM ventilation rate here. Over here we have the flow rate in CFM, and down here we have dates, and the only thing we're looking at here is the stack effect air leakage. And you can see that there are times that the stack effect air leakage or infiltration is more than the required ventilation. On those days, it's not that vital that we have the ventilation going, but then notice there are many days of, especially notice here when the weather starts to get warmer over to the right of the chart. There are many, many days, more than half of the time, there is not enough ventilation in the house, and mechanical ventilation on those days is extremely important. And as we study ventilation and indoor air quality, we're finding that things are more hazardous than we initially thought. The future of ventilation. There was one of the questions that came up earlier. Some of that will be answered here. What about papers? What about research to substantiate the 2013 version of the standard was the question. We're at the point where we are doing more research. There are new methods that can be used now, methods for being able to quantify the detrimental effects of bad indoor air. And the new standard, the 2013 standard, is looking more at indoor air quality equivalence. For the second bullet here, we are getting a better grasp of which contaminants are of concern. We're looking at the health impact of various doses of those contaminants, such as, for example, PM 2.5. PM 2.5 is a particulate matter of the size of 2.5 microns and smaller. These are small enough to embed themselves deeply into the lungs. They come from diesel fuel. The concentrations are higher near highways. They come from cooking, frying. And the more we study these, the more hazardous we find they are. And this is a concept, the DALIs, which down at the bottom you can see what it stands for, the Disability Adjusted Life Year. If we look at a large population of people and we study the indoor air quality and the way it affects them, we can see how their lifetime, their healthy lifetime is reduced if they're living within bad indoor air quality, an environment of bad indoor air quality. And it gives us the capability of quantifying good and bad, the effects of good and bad indoor air quality. These studies will be done more and more as time goes on, and the paper I mentioned that was done at Lawrence Berkeley Labs looks at the disability adjusted life years and shows that with ventilation, people generally speaking, in the aggregate, live longer. But the indoor air quality equivalence concept is part of the 2013 standard, and that will continue in the future standards. It's likely, as I've already mentioned, that ventilation will remain controversial. If for no other reason, there's the health versus the energy issue. Programs requiring ASHRAE 62.2, I want you to know what these are, because many of you who are participating today are involved with these programs. And these are the major ones that I am aware of. These standard work specifications for home energy upgrades, those of you that are working within the low-income weatherization program across the country will be affected by this if you haven't already been. The standard work specifications, here is the website. It took about 3 years to develop these. It was done a DOE contract, and the NREL in Golden, Colorado was the main organization responsible for this. These were published in 2013, and I suggest you go to this website and take a look at these. I think you'll find them interesting, and I expect that these will affect the existing building weatherization industry outside of the low-income weatherization portion of it also. EPA in 2010 published this work, Healthy Indoor Environment Protocols for Home Energy Upgrades. This is this includes the ASHRAE Standard. There's official word from the Department of Energy that they are now requiring the 2010 version of the standard, and they will be requiring the 2013 version of the standard. Various states will have to start using that during the 2014 program year. And finally, the Building Performance Institute will, as far as I know, and this is almost official, will adopt the 2013 version of the standard as of the 1st of next year. It is included in BPI-1200, Standard Practice for Basic Analysis of Buildings, Section 8. That was released for public comment on the 4th of this month. Now the standard. Some details of the standard. This is the cover. This is available at ASHRAE.org. You can view it there, but you can't print it. And of course you can purchase it as a PDF or as hard copy. It's a minimum standard. It's not necessarily a best practices standard, but a minimum standard, which means you must satisfy the requirements. You may exceed the requirements of the standard if you wish. It covers single-family and multifamily residences up to 3 stories, above grade, that is. If it's a 4-story building above grade, it is covered by Standard 62.1. It covers manufactured houses, mobile homes, and modular buildings. It's interesting, if you get a copy of the standard, to read the scope to see what it covers and what it does not cover. 62.2 is a continuous maintenance standard. Now there are many, many standards that ASHRAE has. There are only about 20 of them that are continuous maintenance standards, and this means that they are always changing. As a member of the committee, this is sometimes frustrating. I sometimes get the feel that people on the outside must think that we don't know what we're doing because we keep changing the standard. We do, and I think we do know what we're doing, but there's a lot of involvement from people on the committee, of course, people close to the committee, and others, any of you listening, can submit a proposal, a proposed change to the standards, an addition, a change, a deletion. To do that, you go to the ASHRAE.org website, find the proposed change sheet, and that would be submitted to the committee. The committee must review your suggested change, and then there are 4 options. We either accept it for public review without modification, we modify it, we accept it for future study, or we reject it. Those are our 4 choices if you or anyone submits a proposed change. The design details of the 2013 version of the standard are what I'm going to talk about now, and I'm basing my comments on existing buildings. First of all, it's important to keep in mind that the standard requires local ventilation. Some of you call that spot ventilation, but the word spot is nowhere in the standard. The standard uses the term local, and that is required in bathrooms and kitchens, and I will further define a bathroom very soon. Whole building ventilation is the other part, the other type of ventilation. So we have both of these required by the standard. Local ventilation is quite easy to size and size properly. Whole building ventilation is more complex. The mathematics are more complex for sizing whole building ventilation. There's for whole building ventilation, there's the basic equation, and there's the alternative compliance part of it for existing homes, and there's an infiltration credit for existing homes also, and for new homes, but there's a limit on that. So first, local ventilation. Local ventilation is that the primary purpose of local ventilation is to exhaust air from the dwelling, bad air, smelly air, moist air, air with cooking odors in it, or something like PM 2.5, to get it out of the house as quickly as possible. So generally we think of exhausting air at its wherever the source of the pollution is. Local ventilation is always, without exception, exhaust ventilation. We pull it out and dump it outside. It covers bathrooms and kitchens, and these are the requirements. First of all, bathrooms. A bathroom is any room that has a tub shower combination, a shower, or a spa in it. I'm not sure what a spa is, but I don't think we find too many of those. But a spa would be something like a hot tub. That would have to have local ventilation in it, if a room that had a hot tub. So in other words, a room, a half bathroom as most of us would call it, that has a toilet and a sink in it, would not require local ventilation. For bathrooms, there are 2 possibilities: 50 CFM, cubic feet per minute, demand controlled fan. That's a fan on a switch that the occupant can turn on and off when needed, or it might be controlled by an occupancy sensor, or a 20 CFM continuous fan that runs all the time. For a kitchen, 100 CFM demand controlled fan. 100 CFM demand controlled fan. The best type is a range hood just above the range. Bill, it's time for poll number 1.
Okay, let's launch that poll.
Bill?
Yep, I'm here. Let me just
Okay.
get my thing together.
Okay.
I've made a tactical error here, and the polls are missing. I apologize. I can't launch them.
Okay.
I'll try to put them in
So,
place for the next one
okay,
in the background
that's
here,
fine.
but keep going.
Okay. Okay. I'll be happy to.
While we're at it, we have a couple of, we have actually many questions that have come up in the
Okay.
process. I think this is a good one to tap into your head for. Do you ever think air quality will be part of a BPI in the future?
That's a very good question. I don't know. Air quality is a very difficult issue, and I think that we all understand that air quality is important, but we've had some difficulty in measuring it with equipment that's readily available to energy professionals in the field, such as those that are taking part here. In many cases, the equipment is quite expensive, and the testing requires quite a bit of time. We are indeed doing some of that, and BPI was one of the initial organizations that required testing for carbon monoxide. That indeed is the very important pollutant, perhaps the one that's the most immediately dangerous that we find in the indoor environment. Whether or not BPI will move beyond carbon monoxide testing, I really don't know. Certainly another one that many of us know about is moisture. We need moisture, but it's an issue of too much is not good. That can cause problems. We might get to the point as we measure these indoor air pollutants more and more over time and identify which are the bad ones and which are not so bad, we might come up with better ways to measure them. But of course, even if we have equipment that's available to most people, there is still the time issue. Very often it takes quite a bit of time to do a valid test for various contaminants. Another one that we've done quite a bit with in the energy field and air quality field is radon, which is a problem in many parts of the country. Not all parts, but many parts. I would like to see BPI get into it more than they are now, but I really don't know if they will.
Okay, you can proceed. I'm going to still try
ventilation.
to do this. Yeah, sorry.
Okay.
Proceed.
Okay. Kitchen ventilation. This is a great slide. This is not a good thing to do in the field. Now, this seems very, very strange, and this is obviously a mistake, but the fan in the position it's in is probably much better than a fan that would be in the wall across the room. This one would be more effective than the one in the wall across the room. And we're starting to do studies of the capture efficiency of range hoods. There's been a lot of work that's been done, again at Lawrence Berkeley Laboratory, on the capture efficiency of range hoods. And it could be that within the next 5 to 10 years, range hoods will be rated with a capture efficiency stamped on the box. We're not there yet, but I think we are moving in that direction. And of course, the better the capture efficiency, the better the indoor air quality. As you can imagine, with a range hood, if you cook on the back burners rather than the front burners, say you're frying fish or something, cooking on the back burners, just about any range hood will do a better job of capturing those pollutants than if you cook on the front, one of the front burners. For existing dwellings, and I'm still talking about local ventilation in kitchens and bathrooms, a big difference between the 2007 version of the ASHRAE standard and the 2010 is the alternative compliance path. And it was understood that it can be very expensive to go into an existing dwelling and install kitchen range hood, bathroom fans, and a whole building fan. So what the committee did was come up with an alternative method of complying with the local ventilation requirements without installing local ventilation or upgrading local ventilation in existing homes only. So you may use the alternative compliance path in an existing dwelling only if there's no existing local ventilation, or if the existing local ventilation is less than the requirements of the standard. Those are 50 CFM demand controlled for bathrooms and 100 CFM demand controlled in the kitchen. What happens, as you'll see with this alternative compliance path, is that we develop a deficit. We calculate the deficit of local ventilation in bathrooms and kitchens, and then we compensate for that deficit by increasing the whole building ventilation to make up for it. And Bill, this is poll number 2 if you're ready. If not, I will proceed.
Sorry, I can't right now.
Okay, I will proceed. Another picture of a silly picture. This is not a good way to vent a water heater. Those of you out in the field, I'm sure you have come across unvented water heaters in basements. I've seen quite a few propane-fired water heaters in basements. It's not a good thing to do. Now, moving to the topic of whole building ventilation and the way this is handled in the 2013 version of the standard. Whole building ventilation has a different function than local ventilation. Whole building ventilation is to dilute the air, the stale air in the house, with fresh air from the outdoors. All of us, there's air pollution all over a house. We carry around some of it with us on our bodies. Smells, for example, carbon dioxide, other pollution, maybe from perfumes, deodorants, soaps, those types of things. Furnishings can off-gas pollution, upholstered couches and chairs and carpeting and rugs. Pets generate indoor air pollution. Whole building ventilation is intended to dilute those pollutants with fresh outdoor air. And we will look at some sample calculation using the Red Calc free tool. We'll do some sizing, which will include both local ventilation and whole building ventilation. But what you see in the yellow box on the screen, on your computer screen, is the very generally the method that's used for existing construction to size ventilation. The total required ventilation rate, which is the simple equation that's coming up, you'll see it. We add the alternative compliance supplement to that, and we subtract the infiltration credit. We get the final required mechanical ventilation rate for the whole building. And we will go over that again. That slide will come up again. This table is right out of the ASHRAE 2013 version, ASHRAE 62.2, and the equation at the bottom of the slide is the basic equation Q tot for Q total. It's 3% of the floor area plus 7.5 times the number of bedrooms plus 1. I recommend to you when you're doing your sizing that you use this simple equation as your starting point rather than using the table. The table rounds upward in almost all cases. The whole building ventilation requirements of the standard may be satisfied by intermittent operation. That is, the fan, the whole building fan, is not required to run all the time. Indeed, it may, but it doesn't have to. For example, let's assume you have a heat recovery ventilator, an HRV, rated at 150 CFM. That's the capacity. But the requirement you find of the house you're working with for whole building ventilation is 50 CFM. So that's 1/3 of an hour. So you would operate this HRV on a timer for 20 minutes out of every hour to get an average of 50 CFM. So you may handle whole building ventilation by running it intermittently. And Bill, this is poll number 3 if you're ready yet.
Sorry, I'm having trouble, still having trouble. I think it's a dead issue for this webinar. I apologize.
Okay, I'll move on then. Okay. Now, part of the 2010 and the 2013 versions of the standard is the alternative compliance path for existing dwellings. This, in both versions of the standard, this is found in Appendix A of the standard. It's for existing dwellings only. That's very important to keep in mind. And it's a way to make the standard more flexible for existing dwellings. And we'll go through this, the alternative compliance path. In each room where local ventilation should be, what you do is go ahead and determine the deficit. If there's, we'll go through a few quick examples. If there's no fan in a bathroom, and it would be very difficult to put one in, for example, in my house, there's a bathroom. I have a very old house. It's impossible to get ventilation in one of my bathrooms. So that bathroom has a deficit of 50 in my house. Or if you go into a house and there's a fan there and you measure it, and you must measure it if you're not measuring, you measure its actual flow rate is 37. Now you know when it comes to the time of calculating that deficit. If the actual flow rate is 37, the deficit is 13. You do the same with the kitchen. And for each bathroom or kitchen with a deficit, you can reduce the deficit by 20 CFM if that room has an openable window. Now, it makes no difference if it has 5 openable windows or 1. The reduction of the deficit by 20 CFM is the case. You can't take a reduction of 20 CFM for each openable window. And we'll go through this with examples. You add up all the deficits and then you divide them by 4. And then you add the result of that to the whole building ventilation requirement. For example, if the total deficit is 100 CFM in local ventilation fans, you divide that by 4, you'd get 25. You add that 25 CFM to the whole building ventilation requirement. For existing fans that are to be left in place, there are no sound requirements. You just can keep what you have. If you're putting in new fans, there are sound requirements, and we'll look at those soon. You must measure the flow of existing local fans. This is something that if you're not doing, you would better get accustomed to doing this if you're going to be using the standard, because it is a requirement. Here are 4 examples using the same house and different conditions for the alternative compliance path. This is what a window looks like right here in this very simple plan drawing. Here's a window in this room. Here's the kitchen with no fan, no window, so the deficit here is 100 CFM. Here's a bathroom with no window, no fan, the deficit is 50 CFM. Here's a master bath, no window, no fan, the deficit is 50 CFM. We add the deficits together, 100, 50, and 50. We get 200. We divide that by 4, and we get 50. So assuming the whole building ventilation requirement was 45 before we calculated this deficit, we add 50 to it, and now the whole building requirement is 95. Next example, example number 2. Now we have a window in this bathroom. We have a window in this kitchen, a window in this bathroom, and the master bathroom remains the same. So now the deficit in the kitchen is reduced by 20. It's 80. The deficit in this bathroom is reduced by 20. It's now 50. And this deficit remains the same. So now the total deficit is 160. We divide that by 4. We get 40. We add that to the assumed calculated whole building ventilation, and we get 85. Changing the example more, here's example number 3. Now the difference is, let's assume we have a fan in the master bathroom that we measure at 32 CFM. There's no window here, but now we have a fan in this bathroom. So the deficit here is now 18. So we have a deficit in the kitchen of 80, in this bathroom of 30, and in the master bathroom of 18. We add those together, we get 128. Divide by 4, we get 32. That's added to the example whole building rate, and we get 77. Finally, example 4, let's assume that we add a whole building fan in this bathroom. We still have a deficit in the kitchen of 80. Now we have no deficit in this bathroom, and we still have a deficit of 18 in the master bath, so we get a total deficit of 98. We divide that by 4, we get approximately 25, and now we're down to 70 CFM for the whole building ventilation, and we may put that in this bathroom. So this fan in the bathroom that's running at 70 CFM continuously is now taking care of the whole building ventilation and the local ventilation simultaneously. There's an infiltration credit for existing and new dwellings, and the infiltration credit has to do with the tightness or looseness of the house. For the infiltration credits, you need weather factors, and something that's very nice about the newer standard, the 2013 standard, is that it includes over 1,000 weather factors. Some of you have been frustrated by the lack of weather factors. Now there are 5 to 6 times more than there were with the 2010 version. And the 2013 version uses TMY3 weather data. TMY3 is typical meteorological year. That's what it stands for, 3 data. And I'll show you that when we get to the RedCalc free tool. To find the infiltration credits, you must do a blower door test. The standard states that it must be a multi-point test, but the authority having jurisdiction may allow a single-point test. This is an issue that's a bit beyond what we have time for today, but this is an issue that must be resolved. In most cases, people will be doing single-point tests, I think. You've seen this before, but this is the way we calculate the whole building ventilation. the total required ventilation from the table or the simple equation. We add to that the alternative compliance supplement. We went over 4 examples for that. And we subtract the infiltration credit. The math of the infiltration credit is too complex for me to show to you directly. And then we get the required mechanical ventilation which is the flow rate for the whole building fan. Additional selected requirements of the standard, just a few things I've selected. And by the way, the calculation procedure I think will fall together for you when we look at the tool that's coming up. Something that is added in the 2013 version of the standard is carbon monoxide alarms. Those of you in low-income weatherization and working with a BPI program are already doing this most likely, so this is not new to you. Adjacent spaces such as attached garages, it's important that we ensure that there's not a lot of air movement, for example, from an attached garage to the living space. And that's in the standard, although it does not specify how one is to ensure that this doesn't happen. Labeling and instructions is an important part of the standard. You must label the ventilation fan switch so people know what it is. Something that I think all of you have been doing with your programs is exhausting drier air to the outdoors. This is part of the standard. Sound ratings for fans. If you put in a new fan, either locally or whole building, a new whole building fan must be 1 zone or less. And if it's a local fan, it must be 3 zones or less. If you're leaving existing fans in place, there are no sound requirements. Zone ratings can be found on most fans, but you will not find them on air handlers if you're using air handlers for ventilation, or if you're using inline fans, which are often installed in attics. They do not have sound ratings, and that's not required. Now, we'll look at an example using the RedCalc free software. I hope this ties the calculation procedure together for you. Before we go to the live website for that, you might want to check out these tools. There are more of them. These have been in the works for over 20 years. In the latest version, they're online for you to use. They're free, and we hope, I'm one of the authors of them. We hope that you find these useful. What I did here was I looked at the RedCalc free tools, and this is the 2010 version of the standard. This is the 2013 version, and it's the same house in Colorado. And what I wanted to show you is that the tools look very much the same, and we get almost the same result. Here we have, in the 2010 version, a requirement of 32 CFM for the whole building ventilation, and here we have, here we have 28 for the whole building ventilation with the 2013 version. So the changes are primarily under the hood. They're in the calculation procedures. I'm going to shift now to the Residential Energy Dynamics website. This is the home page, and you can see on the home page there's top-level menu, but also there's a navigation menu over here on the left, and you can go to the various tools very quickly. We are going to use the ASHRAE 62.2-2013 tool. I want you to know that for this tool and All of the others, if you click on the eye in the blue circle that's next to the tool name on the menu, or up here in the tool, it will take you to the user guide. Every tool has a user guide, and this gives you instructions of how to use the tool, gives you tips, best practices, references. So it's a how-to document. And if you're starting at the website, if you go to Getting Started, I highly recommend you do this first. It tells you how to use the tools, what to expect, and how to navigate the website. That's a very good place to start. Now I'm going back to the tool, the 2000 version of the 2013 version of the tool. Scrolling down a bit here, and notice that there is already data in the tool. I was talking with a fellow using it in North Dakota the other day. That's where this data is from. I'm going to reset the tool. I'm up at the top right of the tool. I'm going to reset it, and it zeroes everything out. So now I'm going to enter data for Denver, Colorado. Something I want to point out to you if you have questions about any of the labels here. For example, number of occupants. Notice when I put my cursor over the label, there's a question mark there. If I click it, or if you're using a touch device, you just touch it, and a pop-up tip comes up that explains what the number of occupants means, or the closest weather station. So that's always there, just a click or a touch away, depending upon your device for you to use. So I'm going to start at the top and work down through the tool. We're going to do an existing building. You can see we have a choice of new or existing. And we are going to use the infiltration credit because it's to our advantages. The closest weather station, I'm going to go to the United States. I'm going to select the state of Colorado. And now I select a weather station for the state of Colorado. There are quite a few. You have to scroll to see them all. This is the 2013 version where we have many more. I'm going to select the Denver International Airport. Just a bit of a side here, there's a weather station data tool that I just highlighted in the navigation menu on the website. I'm going to go to that tool, and one of the features of this tool is that it has it's tied to Google Maps. You can turn this on or you can turn it off. I just turned it off. I will turn it on again. For some of you that are near state borders, you might not be aware that the closest weather station is in another state. Now the weather station that I've selected is Denver, Colorado. That's the red dot. The other stations are pink. But what if the house I'm studying is up in Sterling, Colorado, or just north of it? Sydney, Wyoming. Is that Sydney, Wyoming? No, that's not Sydney, Wyoming. What state is that? Nebraska. Sydney, Nebraska might be the closest weather station, so I would use that one rather than one in Colorado. And as I click on it, notice that the map is now centered on Sydney, and the weather data up here changed. So that's a good thing. A good way to initially find your weather station is to use the weather station data tool. I'm going to go back to the ASHRAE tool now, the 2013 tool. The weather and shielding factor for Denver, Colorado is 0.59. The living area, and notice here I have a choice of square inches, square meters, centimeters. I'm going to use square feet. And a feature with all of the red calc tools is math on the fly. I'm going to, this is a place you might use it. For example, this house has two sections. It has one section that's 20 feet by, 10 feet by 20 feet. And it has another section, I'm going to put a plus there, that is 20 feet by, that's a time sign, 40, and another parentheses, and then it's 2 floors times 2. So what I've done is I've entered the two sections of the house, and each of those is 2 floors tall, so I can do my mathematical calculations there. So when I now click or touch outside of that box, the calculation will be done for me. You see 2,000. If I click back into that box, there's the calculation again if I feel I've made a mistake or have to change it. Number of occupants, I'm going to say there are 3 bedrooms and plus 1, so that gives me 4 occupants. The building height, generally we choose, this is a 2-story building. Generally what we use is 8.2 feet per story, so I'm going to put down 16.4. And the measured leakage, this is from the blower door test. This should be what you expect the final blower door test to be. I'm going to use 1600. You may use advanced blower door inputs. I'm not going to do that now, but there is a section for that. We are going to use the alternative compliance feature. And I'll scroll here a bit. I'm going to include the kitchen, so I check that box. And I have 2 bathrooms. You can choose up to 5 for the kitchen. I measure the fan, and I have 72 CFM from the existing fan. And for my example, I do have an openable window, so my deficit in the kitchen is 8. For bathroom 1, I'm going to say there's no fan, but there is a window, so my deficit is 30. And for bathroom 2, my measured fan is 37, and there's no window, so my deficit is 13.
Hey, Rick?
Yes.
We're getting a couple questions about kind of the technical usage of this as well as others, but one question is, so the blower door does not include the roof peak, just the living floor height?
It's a good idea if you, for example, my cursor's up at living area. Whatever you are assuming the living area is, and this is often a question, the blower door number, it's a good idea to have the blower door number equate with that. For example, if the living area includes, if you do a blower door test in a house that has a cathedral ceiling, for example, the top of the cathedral ceiling would be included in the building height, and of course the blower door test would include that cathedral ceiling also.
Okay. There was another question about would the basement square footage be included in the area calculation?
This is it's a very good question. It's a common question, and I think if one feels that if the person designing the system feels that the basement, let's assume the basement is not now part of the living area, no bedrooms down there, no family room down there, but the basement happens to be well connected to the upstairs, then one might go ahead and include the basement in the floor area. This is open to some questions. It's very difficult to calculate, or I'm sorry, to define the living area. And I think something that is important, though, if you're part of a program, for example, part of a low-income weatherization program in a particular state, that state come up with, the administrators of that program come up with rules for determining the living area. For example, should the basement be included or not? Generally, crawl spaces are not included. That's an easier question and an easier answer. But basements can be problematic. The basement generally, for example, in the Northeast, is a part of the thermal pressure enclosure or envelope, but the basement is not lived in. So should the square footage of the basement be included in the living area calculation? I can say that the building height, I can be more definitive with that. The building height is only the above grade height of the part of the building that's within the thermal pressure enclosure.
Okay.
So if there's a cathedral ceiling, the top of the height is the peak of that cathedral ceiling.
Yeah, I think someone just mentioned that if you define the building envelope, that helps with the living space definition.
Yes, that's true. That's true. So we're almost down at the bottom here. What we get, let's look at the results. And again, for results, there are, if you click or touch the label, there's a pop-up tip that will help you out. The N factor, 24.6. This is really not good for much of anything, but it is part of the calculation. Effective annual average infiltration rate, 65. This is in CFM. As you can see, you can change that if you want. If you want liters per second, you can look at it. And by the way, these are also where you have units. It's a good way if you want to do conversions within these boxes, you can do that. But the effective annual average infiltration rate in CFM, cubic feet per minute, is 65. Total required ventilation rate is 90. That's from the basic equation. Alternative compliance supplement. This is how much we have to add to the 90 because of the lack, because of this deficit right here in local ventilation. The infiltration credit for this house is 65. We subtract that, and the total for the whole building ventilation fan is 38. Now, I'm going to ask a question. What do you suppose will happen to this 38 requirement if I tighten the house by taking this down to 1200? Now the measured leakage is 1600. If I take it down to 1200 and click outside the box, you can see now this goes up significantly because the infiltration credit is now different. There's less air coming from natural air leakage, so we have to provide more for ventilation. And finally here, before I open it up to any question, one more part of the tool, the whole building ventilation runtime tool. This is an add-on for the 54 that's now required here. What if our fan is a 110 CFM fan that we have on hand? We put that in here, and we find that we have to run it about 30 minutes every hour to get an effective ventilation rate of 54. So that's what this is for. It's a design help. So Bill, I think now let's open it up to any questions, if there are some there.
Oh yeah, there are a bunch. One comment, a helpful comment, per the Missouri Department of Economic Development, the basement is concrete, then it is a conditioned living space even though there are no bedrooms in that area. So there's one state definition there. Yes, and that is the case in many places. So the basement would be considered within the thermal pressure enclosure or envelope or boundaries, and generally would be included. Some would say, and I wish I could give a very clear answer on this, but I must be honest, and this is something the committee has been working on, the 62.2 committee. If no one is living down there, should that square footage be included?
And especially if the basement is not well connected to the upstairs, but it is part of the thermal pressure envelope, should it be included, because if you do include it, your ventilation rate will go up. For example, let's just do a quick example and say that the basement is another 1,000 square feet. Let's see what happens. Now we have 54, and now we go up to 84 by including the basement use. So you can see this can be a significant issue in places like Missouri or other places that typically have basements. It's an issue that must be thought about.
Okay. There are a lot of questions referring to implementation, as you might expect. One of them is, what if a major remodel is happening on an existing building? To use the existing guidance or the new guidance?
That's a good question. If it's major remodeling, this is often covered if there are codes in the state. The codes generally refer to new construction and not existing. Many states are using the international codes, the package of codes like the International Energy Conservation Code or the International Building Code. There is an international existing building code, and if a state has adopted that code, then often that defines what one must do if there's a significant renovation. The ASHRAE Standard itself, 62.2-2010 and 2013 versions, are silent on that issue. The standard refers to existing buildings that were in place at the time the standard took effect and new buildings. So it doesn't define existing and new other than in that manner, and it does not say anything about significant renovations.
Okay.
So that's a question I can't answer in detail.
And again, another question about implementation, in particular with rental units. This one viewer mentions running a ventilation fan usually, in his experience, means a direct power vent water heater is required to overcome backdraft situations, and that presents an economic challenge for the landlord. Do you have any comments or reflection on that?
Yes, it's not only an issue with rental buildings, but with owner-occupied buildings, single-family or duplexes, whatever it might be. Running a fan uses energy in a couple of ways. One is the electrical energy used to operate the motor. Some fans these days use very, very little, as low as 14 watts, 17 watts, and there are others that are much higher, like 90 watts. So it's a good idea to look at that when installing a fan and purchasing a fan, and using an Energy Star rated fan is a very good idea. You find that the better fans use much less electricity, but they're also more expensive. The other cost of running the fan is the air might already be conditioned, either heated or cooled, and if you run the fan, of course, some conditioned air is going to be expelled to the outdoors, or unconditioned air will be drawn to the indoors. Both of those will happen simultaneously, and there's a cost involved there. A way to minimize that cost is to use heat recovery ventilation or energy recovery ventilation, but that equipment is more expensive and the installation is more expensive. So there are costs here, there are costs involved here that must be taken into account.
Okay. There's another question back to the program itself, or to the RED tool. Can you save data for future editing on RED?
RED Calc free, you can save data. There will, within the next year, be another version of this called RED Calc Pro, which will not be free. It will be available by subscription, and you will be able to save data. At this time, with this tool, you You can load this. I'll give you a few tips, behind-the-scene tips. You can load this on your computer when you have an internet connection. On your computer, your iPad, your smartphone, whatever your device happens to be. You can then use this out in the field where you do not have a connection. You can do 10 different calculations in a day, for example. But you cannot go to another tool, and if you close it, you will eliminate that tool from your cache. So as long as you keep it open and go out in the field, you can use this without an internet connection. As far as saving the RedCalc free tools, if you're using a smartphone or an iPad, I know those tools best because I have an iPad and an iPhone. You can easily take a picture of the screen. So with this on the screen, you can take a picture of it, and then you can email that, you can print it, you can save it to a file. So that's a rather elegant, but on the other hand, crude way of saving data. You're saving it as an image rather than anything else. With RedCalc Pro, you will be able to save you'll be able to save files, name them, save files, but you cannot do that with RedCalc Free.
Okay. We have a couple more questions. Well, actually, as I said, a lot of questions here. One is about radon, and I think you addressed it the last session. You could address that again relative to impact on radon.
The radon is very often, the primary source is from soil gas, the ground, and other sources from water, from wells, from individual wells, but that's not as much of a problem. When we install any device in a house that creates negative pressure, a dryer, for example, that we vent to the outside, that's an appliance that draws air out of the house. A whole house vacuum system that has the canister outside in the garage. A fan in the bathroom, a whole house ventilating fan in an attempt to comply with the ASHRAE standard. All of these things create negative pressure. There is some evidence that that can increase radon concentrations within a structure. It's not always the case because, remember, a ventilation fan also brings in fresh outdoor air. So there are more studies being done, but I think it's a good idea if a house does have a radon problem that be treated separately. Radon mitigation and sub-slab ventilation for that radon mitigation, and that be done separately. I do not know of any cases where adding fans to comply with ASHRAE has taken a house, brought a house over the threshold, usually 4 picocuries per liter in the living area for radon. But I imagine that there are cases out there where this has happened. In such case, one would have to mitigate the radon with a special mitigation system.
Okay. Another question here with regard to adjustments in the calculation for appliances that use indoor air for combustion.
Well, there's no difference in the calculation for that. The calculation would be done the same. But it's very much like the radon question. If you add fans, if you add local exhaust fans, and if you add a whole building fan, if you're currently in the initial state, there's no backdrafting, there are no issues, no spillage issues, for example, with combustions, the appliances that are not direct vented. You might start having trouble because often when these fans are installed, the house is also being tightened. It's part of the weatherization process. As the house becomes tighter, it is more, those existing appliances are more likely to spill. And then as we add ventilation fans, that can make the situation even worse. So it's very important that post-weatherization combustion safety testing be done, be engaged in, to make sure that when we leave the house, we're leaving it in a safe condition.
Okay.
Let me add that it makes it even more important to do one's best to install direct vent appliances if the money is there to do so.
True. Another question Andrew's asked actually a couple times here, I apologize, but he's asking for HERS ratings on a 4-story multifamily building. Should we use 62.2 or 62.1, and what are the differences?
It's a good question. That's a bit too much for me to handle. First of all, I don't have a very great knowledge of 62.1 standard. Secondly, I do know that there's an effort going on to look at buildings that are on the margin, for example, 4-story buildings. Technically speaking, at the current time, a 4-story building, 4 stories above grade, multifamily, would use ASHRAE 62.1. That's a significant change in the ventilation required. And there are many buildings out there that are the residential buildings, 4 stories, and the two committees are starting to talk together more, the 62.2 committee and the 62.1 committee, and try to come to an agreement for some language that would handle buildings that fall almost in between the two standards, because now it's a significant difference between the two. And if nothing else, that has to be justified. But I think what will happen, the outcome will be perhaps some language in both 62.1 and 62.2 that handles buildings that are 4 stories.
Okay.
But I really don't know I have anything concrete on that yet.
All right. There's a question about specifications or recommended ventilation systems. I was going to offer the Home Ventilation Institute and Ventilating Institute as a resource.
It's a very good idea, yes.
Okay.
And I think the website is hvI.org.
That's exactly correct.
Yes.
Yeah, so that would be a
place
good
to go.
Yep.
Yes.
Another important question we seem to get a lot is, does the 2013 standard pertain to mobile homes and manufactured housing? And then kind of a follow-up, did the 2010 pertain to the same housing?
Both versions, 2010 and 2013, pertain to mobile homes and manufactured housing.
Okay. Very good direct answer.
And the person asking that question might be working with weatherization, that low-income weatherization, that comes up often. And as far as DOE is interpreting the standard, they are saying, yes, it does apply to mobile homes and manufactured housing and low-income weatherization. And that's what the standard, in its scope, states, that it does apply to those areas.
Okay. There is a question about measuring range hoods, making measurements in range hoods. And I know our previous presenter, we had Paul Raymer, had a method that I was going to share. But did you have any advice on that, Rick?
I do. Sometimes measuring range hoods is difficult because many of us use an exhaust fan flow meter from the Energy Conservatory and a digital manometer to measure bathroom exhaust fans. And it can be difficult measuring range hoods. First of all, the exhaust fan flow meter, one thing to remember, it only gives you a reliable measurement at 124 CFM and lower. And a range hood opening is often much greater than the opening of the exhaust fan flow meter. So therein lies a problem. And most existing range hoods will be greater than 124 CFM. But what some people do is use cardboard or a piece of plywood, put it over the range hood opening, and then put their exhaust fan flow meter over that. If another way I've used in the field, and I promote the use of a pitot tube. I'm now, if you look at your screen, there's a red calc-free tool for pitot tube use, and I'm going to the user guide because it has a picture of a pitot tube. Here's a picture of a pitot tube right here, and you can get these from a place, for example, W.W. Granger. I think most of you have access to them as a supplier. They're made by Dwyer Instruments. They're about $60.
Or TruTech Tools.
Oh, you have them. Oh, great, Bill.
Yeah.
Okay, that's wonderful. Is $60? Is that the right?
That's about right.
Bill?
49 to 100. Yep, in there.
Okay, and if you use if you get a pitot tube from Bill from TruTech Tools, it's a great device. It's an underused tool. I think it is the gold standard for measuring airflow within ductwork. And then with that, here is the red calc-free pitot tube airflow tool that will allow you to get the airflow rate. It's great for dryers, but if you have access to the ductwork in a kitchen range hood, and if you can get the pitot tube in that ductwork, you can get quite a good idea of what the flow is from that kitchen range hood. I like it better than any other way, but as many of you know, sometimes you just can't get at the ductwork in a kitchen range hood. But if you can, a pitot tube is a good solution.
Let's see. Can you make any predictions, or does your tool or depressurization caused by mechanical ventilation that runs at different flow rates if you have, say, a home modeled in your system?
What you can do, there are other tools here, and what red calc-free tools are trying to do is bring building science to the web, and we're trying to come up with tools. You can do that with the advanced infiltration tool. This is set up for the same, here it is over here under air leakage, and it's set up for Colorado right now. And it will give you infiltration rates, and even if you come down here, infiltration load on the heating system. Soon we will be adding ventilation to this, but now you can get some sense of what's going to happen, and you can choose for the information here. It's too much for me to really explain now, but you can choose your date range, or with your touch device or your computer you can select the date range on the chart, as I've just done, to zoom in on something, and I can zoom in on even more, and you can look at stack effect, wind effect, and so on. But this tool, you might, the person asking the question might check the advanced infiltration tool and the design infiltration tool to get an idea of just what's happening with infiltration. And of course, attaching a fan, you could simulate that with this tool, and soon, as I said, with the advanced infiltration tool, we will include ventilation in that tool.
Okay. I have a question here. I think it's related to what we're talking about now. Are you familiar with the term SWS? I was going to ask the asker of that question.
SW, yes I am.
Okay. SWS has a room pressure test post-mechanical venting. Is that something that's typically addressed?
SWS is the standard work specifications, and these are early on in my slide presentation. It was the first bullet on a slide, the DOE NREL SWS, those specifications, standard work specifications, and I think there's a room-by-room test in there that if the air handler is running, that it's a good idea to ensure that the pressure difference across the door is 3 pascals or fewer. I think that's what the questioner is asking about, although I'm not certain.
Okay. And then there's always the question that's been coming up a lot here throughout the course is about where does the air come from? Where does the fresh air come from? Where does the makeup air come from when you are doing the ventilation?
Generally speaking, remember, for local ventilation, it must be exhaust only. For whole building ventilation, it may be exhaust only, supply only, or a combination of the two. A combination of the two, an example of that would be heat recovery ventilation that exhausts and supplies air. Let's assume that we're exhausting only, which is recommended for northern climates, colder climates. If we're exhausting only, we cannot be sure where the air is coming in through the building envelope. We can't be sure. We don't want it to come in from the garage or a crawl space that's got bad air in it or a basement that has moisture problems. A disadvantage with exhaust ventilation is that we cannot be certain where the air is coming from, the fresh air, and we hope it's fresh air. An advantage of supply-only ventilation is that we have the capability of filtering the air, and we know where it's coming from. And by the way, there are studies that show that if we have exhaust-only ventilation, the envelope through which the air comes does have a filtering effect on the air. It does catch some of the particulates that come in from the outdoors. But we can't be certain where it's coming from through the envelope. So that's a disadvantage of exhaust only.
Okay. And one follow-up question, that by saying exhaust only, does that preclude HRVs or heat recovery ventilation in the bathroom?
It does not, but if one uses those, check with the manufacturer to make sure that this is an acceptable use to take air out of the bathroom, and of course then you'd be supplying usually an equal amount of air somewhere else in the house. But this is, I think with most manufacturers, this is an acceptable use of their equipment.
Okay. Do you have a price range on whole house ventilation systems, both HRV and ERV?
I do not. I do have a price range on complying with the standard, but I'll take a guess at that. But first, this one. Wisconsin, the weatherization program in Wisconsin has been using the ASHRAE 62.2 standard since 2004. And they have installed it in about 20,000 houses to date. And they have found that the cost of compliance is around $600 in their low-income program. They have installed a few HRVs, ERVs. My guess is that the cost of those is going to be more in the range of $1,500 to $2,000. That's a guess. I do not have good data on that.
Okay. In a new home, can an HRV take the place of a local exhaust fan if the HRV is sized correctly?
Yes, I think that's very much related to a question that I just dealt with. As long as that is acceptable to the manufacturer of the equipment to draw air out of a bathroom, manufacturers generally will have more of an issue drawing air out of a kitchen because of the potential for grease.
Okay. As an auditor, range hood fans always fail worst case spillage in the CAS. What is standard advice to the homeowner with knowledge that backdrafting may occur when the fan is on? I know this is the heart of the controversy between ventilation and health.
Good question. I think it's very important that you solve any problems with combustion safety with the venting of combustion appliances along with installing ventilation. If you install a range hood, it's a good idea to make sure that it's not overkill. There are many of them that might be 800 to 1200 CFM, and that is far in excess of what the standard requires of 100 CFM. But if you have a sense of how much that range hood is drawing, perhaps you can lower the speed if it's causing problems. You can measure that with a pitot tube if you're able to access the ductwork. Pitot tube and the Red Calc free tool for pitot tubes. But this is an issue that will continue to come up, and in some houses, the tighter the house, the more likely this is to be a problem. And often what we find is that in higher end houses that might have commercial grade ranges, they might also have commercial grade range hoods that are venting much more than they really need to comply with the standard. So in such cases, makeup air should be brought in, and there is advice in the standard about makeup air.
Okay. I think we're going to do one more question, and then I'm going to forward the list of questions to you, Rick, for your reflection. And there's a lot of good stuff still out there unanswered, and I think there's still a need for doing this. And we have discussed doing this again. Rick was offering to do this again for free, I believe, in early December. So yes. Look for that information. The last question I'll ask, and I'm going to do a quick commercial for TruTech. When will this become part of code? And I think that's a very broad question.
It's a broad question. It first became, the ASHRAE Standard first became code in the state of Maine for new construction. The state of Maine adopted the 2007 62.2 code for new construction only. And then California adopted a version that falls in between. It's a more complex version that falls in between the 2007 and 2010 version. But if you are working within a DOE program, essentially low-income weatherization, for example, it is essentially code now in the work that you are doing. It's not a local code. It comes from DOE. I think we'll find over time that states slowly adopt the 62.2 code as a code. But as far as I know right now, for state codes, Maine and California are the only two states that have officially adopted the 62.2 as a code.
Very good. Okay, I'm going to take control back over. Did you have any closing comments, Rick, as I do so?
No, I think not, Bill. Good questions. Thank you for everyone that asked questions, and thank you for attending.
Okay, so right now we're just going to do a quick overview of some additional resources and materials. Rick has talked extensively about his project. He and Charlie Holly have developed this Residential Energy Dynamics program, RED. You can find it at residentialenergydynamics.com. It's an online tool that you can use to do an awful lot of calculations. I think it's a real asset for the industry. We also talked very briefly about the Home Ventilation Institute, the HVI.org. Here you'll find product information about ventilation fans. And there's also the TruTech website where we talk about the measurement instrumentation. Specifically, I want to direct you towards, if you look at the top of the page, there's a tab called Videos where we go through and provide training videos on product evaluations as well as usage of various products. Many of them, as I'm showing here, in the airflow arena. To do hot wire anemometers, to do static pressure tests, vane anemometers, etc. In addition to that, we do have a selection of airflow measurement tools, and we've got them broken down into subcategories. So this would be at trutechtools.com/airflow. You'll find anemometers, capture hoods, pressure matching, true flow devices, differential pressure, pitot tubes, as well as other training tips and techniques. You can get to this various ways, but you can also get to it here. We do have some airflow training where we take some of the most common methods of airflow training and break them down and give you some some information on how to do these various types of tests. You're attending today a webinar. You can find more of our webinars. We offer a wide array of them, adding and changing them all the time. You'll see there are ones that are coming. The one for today is mentioned on the events calendar, which is truetechtools.com/events, and you'll find that right here on the events page. Just click the events link. So if you want to look into getting some instruction on the use of the measurement equipment, we provided various types of equipment, anything for energy auditing your HVAC work. I think we're going to wrap it up now, and there will, if you go to the TrueTech Guy blog, it's truetechguy.com, you'll see that Rick's slides are already up there, and I'll be sending up an email afterwards to send a link to this for everyone. The slides are already up, and the recording, which is going on right now, and we'll be stopping shortly, will also be available on our YouTube channel, and our YouTube channel can be found here at youtube.com/JimBergman3. Jim's my business partner at TrueTech, and you'll be able to find various videos, webinars we posted up here. So I want to thank everyone for attending, and any final comments here, Rick?
No, Bill. Thank you, everyone, for attending, and thank you, Bill.
Okay, you're welcome. Take care, everyone, and please send us any kind of emails or questions that you have, and I'll make sure Rick gets those questions. Take care, all. Bye. I'll stay on for a couple more minutes, and I'm going to answer a few more questions that are coming up. So if you have a question that I can answer in the next 5 or 10 minutes, I will do so. So we're just going to say stay static on this screen, and I'll be answering questions in order to leave the system live. But the session's officially over.